Oh, what am I doing here? Morning, Ben. Hopefully you're not alone. Well, I guess it doesn't matter. Oh, here we go. Okay. Good. There are two of you. Good enough. So, I guess it's 8:30. I better get started. So, this is from last fall. I just need to grab a picture of Dora in a hurry. That there aren't boats like this in the Northwest Arm, other than the one I pointed out last week that's sitting here that sat there all winter. And no, that's at Coburg, that's Dal. So St. Mary, the Loyola building isn't in the distance here. So here's this morning, though. I'm in Kingsburg. You can tell I got a white background, means I'm in Kingsburg. And the sun was just, it was gorgeous this morning around 7 o'clock or thereabouts, just coming up. But red sky in the morning, sailor take warning. It means we're going to have a rainy, stormy day with a red sunrise. And this was yesterday afternoon, just down the road from where we are, looking across Kingsburg Beach at the Hell, it's called, on the other side. And there must have been about 20 deer out in a field. I've seen up to about a dozen there before. It's a popular spot for the deer. But there must have been about 20 yesterday. It was quite surprising. Gorgeous day yesterday. And I hope you got out and enjoyed the sunshine because we're not getting it today. So let's get on with the show. Hello, where's my slides? They're not moving. My slides are stuck. Can I go backwards? Yeah. Can I go forwards? Go any further forward? Okay, we're using Plan B then. That I'm just going to switch over to PowerPoint. And that's where the next slide is. Let me, can I get this out of the way? I will shrink this down. There we go. I've periodically had this problem before where I end up having to go and actually put PowerPoint up but not use the slides within Top Hat. So a few things before we get underway. Questions 6 and 7 on the test. If you remember those, they were two scatter charts I gave you and asked what you thought the correlation was between the two variables. Was it positive, negative, weakly, strongly positive or negative? Was there no correlation? And it turned out there were ones where it was, I think, weakly negative or weakly positive. But many people, I'd say half, said that there was no correlation they saw there. And then there was one that was moderately negative correlation. It was around a 0.5, 0.6. But most people thought it was very weak correlation. And that, I think, was like a landslide, everybody picking that. So it's apparent that learning how to interpret those charts and the level of correlation takes a lot more experience than you're going to get when you've just been exposed to it briefly. And so we changed it so that it accepted two answers instead of one answer. And that boosted everybody's grade significantly. I think the average is somewhere in the vicinity of 13 or thereabouts on the test now out of 16, which is pretty decent. So you should find that revision took place. I've still got a group of students that missed the test or the quiz or both. I've been giving extensions before for those sorts of things. In a couple cases, there are people that it maybe just aren't there anymore. But if there are extenuating circumstances why you could not do one or the other, if you'd contact me and we'll look into that case. Assignment 3, I've posted that uh, I had a few questions over the weekend. I actually had them by Thursday or by Friday morning. I was having questions on the assignment. So there are some keeners among you that start work really early on assignments, which is amazing and is really good. I'm pleased to see that. But I expect that most of the questions are going to come up over the next couple of days. So like the previous 2 assignments, I'll devote the beginning of Wednesday's class to fielding questions about the assignment. You're still welcome to email me if you've got questions. If it's uh, uh, the Keeners don't have kids. Yes. uh, uh, that you're welcome to email me with questions, and I recommend generally if it's, Excel is not doing something you think it should be, because it's an Excel heavy assignment. Send me the spreadsheet. Don't send me screenshots, because I can't see what's happening underneath. That your screen is showing an error or showing numbers or something that's wrong. But to find the cause, I need to actually look into the spreadsheet. And most of the time I can find it quickly. So send me the whole Excel sheet. But we'll talk about it on Wednesday, and I'm going to adjust the Wednesday's lecture accordingly. And the other thing is I've got an electrician coming sometime this morning. He was supposed to come last week, but didn't. And there is a distinct possibility he's going to mess up my internet. And if that happens, then I will re-record the lecture and post it. Okay, but hopefully we won't get any interruptions and get going. So last class, we started out building a model that it was one to predict those credit card balances. And we started trying to improve the model, and we did it by adding new variables that we went through. First, we added limit, and it turned out it didn't work. It didn't do anything because both of them were really correlated with one another. And we even found when we added income, we had issues. And this is a problem called multicollinearity, that it happens when you've got 2 variables or more that you're trying to use to make predictions that are strongly correlated with each other. I've not discussed it in your current assignment, but if you go and look at it, what I've done is collected uh, house sales data on a little over 80 sales that happened this last year in the west end of Halifax, and about what the selling price was for the home and a bunch of characteristics of the home. But you may well find that bigger homes have more bedrooms, bigger homes have more bathrooms, bigger homes tend to be on a bigger piece of property. Those things are correlated with each other. So it may be that once we've taken into account the size of the house, that if we add in the number of bedrooms, it doesn't tell us anything new because the 2 of them are correlated. Or it may add it in a way we don't expect. I don't think it actually does in that data set, but it would be a real possibility. And what I'm recommending that you do, and I'm going to emphasize today the process of building a model, that try to do it incrementally. Add one piece at a time so you see what you're doing, and add things that you think are going to improve predictions. You're going to improve the predictions by reducing errors. Errors in regression are called residuals. So let's see if we can explain the residuals and build a better model. And we just keep doing this over and over again. So today I'm going to look at them, but looking at 2 different issues from what we looked at last time. Now I'm going to look at should I use a straight line? because maybe I should be using a curve. So maybe that's where my model isn't doing well because I restricted attention to straight lines. But the other is I restricted my attention to variables that were numeric. What if I use nominal variables? What if I took account of marital status or gender or something like that? Could I make a better model? So, and then I'm going to talk back about sort of summarizing this with issues and summarizing the process. And the process is the big takeaway. Okay. So first, those residual plots that, just to recap, those generally come out of Excel. You can request them when you fit a model, and it will take each of your variables and plot the errors in prediction versus the variable. And so our very first one that we did, our first model used rating to predict balances. And when you look at the residual plot, you would see there's something strange over on the left. And this had to do with balances that were zero and people that didn't owe anything on their account. That we didn't allow negative credit card balances, and they don't happen very often. So maybe there's something we can do about that group. We won't, but it's something to think about. That then we looked at adding income as a variable, okay, because it would help us explain things better. And when you looked at the residual plot for rating, it changed. It still had the thing on the left, but it looked different. Okay, it looks sort of sharper going down, and then you can see it here. That looks like a bit of a goes down, curves, goes up. Now it's a little fuzzier going down. It's not just a straight line, but it's more pronounced going up again. So there's a U shape here, and then the U doesn't go up over here, it flattens out. So it looks like it goes down, up, and turns again. It's got two bends in it, two turns, and that's important. How often it bends is going to be one of the things you'd look for in a curve. The other is, yeah, there was some scatter up here, but there was scatter down here. Now, though, we've got scatter up above that's different from this S. So it's different from the curve. So there seem to be two things happening. And we're going to look at those two today. If you looked at the scatter with income versus the residuals, that you get the main scatter here, okay, between those two lines. That looks like, and it looks pretty ordinary, except it's a bit low. And then I've got a cloud up above. I've got an outlier group, which is something that you don't remove outliers, you try to explain them, see what's going on. That I know a lot of people think, oh, outliers, let's discard them. And that was sort of what we did earlier in the course. Outliers you set aside because they're not typical, but they are ones you investigate. And that's what we're going to do today is investigate the outliers. So back to the curviness. So this was our original scatter plot of credit score rating. And we put a straight line. And I think I told you it looks sort of like an S, like it sort of goes up, slopes, and then turns like a stylized S. And now my residual plot really seems to highlight that. And so how do I go and capture a curve? Because the technique we're using is called linear regression. So it's a method based upon straight lines, not a method based upon curves. So generally, because I like simple models and keeping things simple, and there are lots of curves. There's so many different types of curves. There's sine waves, there's log curves, there's exponentials, there's ratios, there's you name it. There are all kinds of them, but they get complicated, and we have no idea what curve to use. Ours, why don't we just try using something simple on it, a simple curve. If it was U-shaped, just like that, and nothing else, we call that concave up, then a quadratic would work, something with an x squared. But mine has two twists. So a second twist, I'm going to need to go to x cubed, a cubic thing. Polynomials are really nice, simple functions. And I like them because notice the different terms are added together. Okay, so we've currently got a linear function. It's got an intercept and it's got a straight line portion. I could create two new variables, an x squared variable, an x cubed variable. So I'd have three variables. Instead of one, I make it into three. I could have rating, rating squared, rating cubed. And then I've got a linear relationship among them. And that's what's nice about polynomials. Brings me back to a linear function. Linear ones are where the terms are just added together, an additive function. So, but I got a problem with this, and it's a scale issue. Ratings go up to 1,000. So a rating squared goes up to 1,000,000. Rating cubed goes up to 1,000,000,000. So I'm going to have some numbers that are big, 1,000, some that are really big, and some that are just absolutely enormous. And the coefficients are probably going to end up going from 2.57, like we might have had initially, to 0.00 something, to 0.00000. They're going to be tiny because I'm multiplying by a big number. My coefficient's going to be a super tiny number. I don't like all that. And it's often recommended that in every case, some people do it with every variable. They scale them so that they're of similar size. And I'm not going to get into that as a big deal, but some researchers recommend that you always scale your variables. So some variables use big numbers, some use small numbers, that they, like in this one, income was measured in thousands of dollars. So it scaled it so that the numbers were smaller. So you'd get 20 instead of 20,000, or 100 instead of 100,000. So it got them down into manageable numbers. So scaling is a very common practice to get everybody having very similar units. How do you scale? There are different methods people use for that, but the most common one is a thing called a z-score. It's actually based upon bell curves and the normal and all that stuff. And so take the rating, subtract the average rating, the mean rating, and divide by the standard deviation, and you get a z-score. And most z-scores are between -2 and +2. I don't know. It's like saying that most of your data is within plus or -2 standard deviations. That's, if you do the math, that's really what you've got. Z-scores tend to be between -2 and +2. Sometimes you get some z-scores that are 5 and 6 because you've got very bizarre values in there, but they're uncommon. Most of the time it's between -2 and +2. And so if I were to square them, I'm going to get between, well, squaring them makes them all positive. They're going to be between 0 and 4, most of them. If I cube them, they're going to go between -8 and +8. Hey, those are all manageable numbers. They're all modest size things. And so that's what I'm going to do. What I'm going to do is go into Excel. I'm going to work out what a z-score is. I'm going to square it, and I'm going to cube it, and I'm going to create those as new variables. And so this is what it looked like in Excel. And we'll flip over to that in a minute. I'll go and show you what I did. Okay, so I took the rating score here and I created a z-score for it. Okay, so a rating of 283, that's below average. The average was around 500, something like that, or 350, I think. And So when I calculated the z-score, it was negative because it's below average, and I get minus 0.46. 483 is above average, and so it got a z-score of 0.82. When I squared minus 0.46, I got plus 0.21. When I cubed it, I got a minus again, and I got minus 0.100. So it keeps the sign appropriate. Okay? And I did that with each of them and created these extra columns. So now I've got one variable that's X variable that's going to be income, one that's rating, one that's the Z squared, and the other one that's Z cubed. And so these four variables I'm going to put into my model, and here's the results I got back. Okay, let me see if I can find this thing here. So I've got so many tabs now here on this guy. Let me move over here. Okay, so here I am. Let me make this bigger so I can see it. My keyboard's not responding here. Now, I know you're not getting to see my lovely face here. There I am. I'm back. Okay. So, as I said, what I did, initially I had income and rating in my model, and I had balance in my model. So initially my model had those two variables to predict balance. So I created this column, Z rating, and I took the average and I divided by the standard deviation. I saved them down below. Okay. And then this one is, I just took that value that was in F2 and I squared it. And this one, I took the value in F2 and I cubed it. Okay. And then I went and I did data analysis. I went and did, hello, where are we here? Regression. Okay. And it asked me, where is my Y range? And I gave it column E. E1 to E401. If you remember, we had 400 values we were looking at, and we have labels in the top row, so 401 rows. My X's are now in columns A1 all the way across to D1. Okay. Oops, sorry, D401. And then I'd tell it I had labels. I put the output in H1. I clicked off that I wanted residuals. So I did all these sorts of things here. I clicked OK, which I'm not going to do because I've already done it. Let me just scroll across to what I got. So it ended up with an R square of 0.894. 89% of the variabilities was explained. That, I don't know if I've still got it. There it is. Hello. Why doesn't this want to make itself bigger? Sorry, I can't make it bigger for some reason, but it says 0.875. Okay. And so before, my R square was 87.5% with a standard error of 163. And now I've got an R square of 89%, little improvement. My standard error went from $163 to $150. So predictions before were going to be off by probably $163. Now it's $150. It's better, but not an awful lot. I wouldn't get excited about it, but it's better than we had before. Okay. That if you look down at the model, it's going to end up with different coefficients. It's thrown in coefficients for the rating squared and rating cubed. Okay. I'm going to raise this as an issue later at the end as to, we did indicate it last time when we were looking at income. Trying to go through to make sure if you're adding variables that they're important, that they're contributing, look to see if their coefficients could be zero. So income -9, standard error of 0.4. So my best guess of the coefficient is -9, but it might be off by 0.4, might be off by even 0.8. But still, that means it's at least -8 to -10, something in that range. So income is important. Rating, 4.3, standard error, 0.097, so it might be off by 0.1. So maybe it's not 4.3, maybe it's 4.2, maybe it's 4.4. It's bigger than 4. It's important. Something's happening. If I look at the squared term, was it useful to add the squared term? Didn't seem to make my model a lot better. Well, my coefficient is around 81, 82. Standard error is 9.7, say 10. So maybe this coefficient shouldn't be 82. Maybe it should be 72. Maybe even 62. Maybe it should be 92 or 102. But it's still between 60 and 100. It's real. It's not zero. I'm not looking, could it be a positive coefficient or a negative coefficient? It's not shoving me down into negative territory. So it's real. And the last one, rating cube, it's got a negative coefficient. I have no idea what these coefficients mean because I don't know what rating squared and rating cube mean. It says -21, standard error is 3. So I could be off by 3, might be off by 6. So maybe it's -15, maybe it's -27. It's negative regardless, and it's kind of big. So this is telling me that all of these variables are important. If any of these ones had gone, maybe it's positive, maybe it's negative, throw it out. It's probably not telling you anything. Okay? But ones that are consistently negative or consistently positive, those are important variables. You keep them in. If I looked at my residual plots, my one with rating, it's still sort of twisty. I guess if I made it scale changed, you can still see twist to it. But look at these guys. What is going on up here? This is strange. So something is twisting this around, and maybe these guys are causing part of my problem here, making it hard for me to get a good curve. What about rating squared? Looks pretty flat, but it's got funny ones sitting up here. Do I have some other plots kicking around here? Where are they? There should be some more. Oh, there they are. There was rating cubed. Not sure what to read out of here. I've got some really high ratings when cubed. They became super big. That and over here, I've got these odd guys looking again. And income looks sort of fine, but I'm troubled by the outliers. So what do we do about those? Let's see. Make sure I've got the right PowerPoint back again. So what do we get next? So, oh, there I've got it. So my R square has gone, has improved. This was the old model. This is the new one. I've gone from 0.875 to 0.893, 894. Yeah. That my coefficients have changed. My standard error is smaller. It looks like having the extra variables has led to some improvement, I should keep it, as long as you don't mind working with 4 variables now instead of 2. But it's still not a huge improvement. Okay. You'll notice some of my coefficients have changed a lot. You know, the -7 is now -9. The 3.94 is now a 4.3. These are bouncing around because these 2 variables are quite correlated with each other. That's why this guy is negative on income. And so throwing in some more variations on ratings is disrupted the coefficients for the other variables. That they we've sort of gone through that type of thing. It's still a problem when we've got a nonlinear model, that going and transforming the variables like that isn't going to take away the fact that rating and income are correlated with one another. That's still going to be a problem for me. And said, I've still got some twistiness here. It's a little better. This one seems to have more twist than this one does. But these outliers bother me. Okay? And they look like a whole group among themselves. And maybe that's what I've got. Here's one group of borrowers. They're nicely well behaved. And then I've got another group of credit card holders that are different. Maybe that's the case. Maybe it's something else. But that's the first place I'd look to see when I've got a whole pocket of outliers. Because I've got another variable. Male, female, married, yes, no, student, yes, no. Or say this was American data, and there they traditionally classify them by ethnicity. Actually, I don't know if they're allowed to collect that for credit. I know they're not allowed. Actually, they can't use gender, and they can't use ethnicity in making lending decisions, but they still do indirectly. Actually, because of multicollinearity, they are still biased against female borrowers, and that non-Caucasian borrowers are still discriminated against in lending. But let's look at these and see if we can see a pattern in the residuals. So this isn't a standard residual plot, and it's not one that I can do. Before we took residuals and we looked at correlation with the other variables. These aren't ones I'm going to look at correlation. So I'm going to go and do this by looking at box and whisker charts. Okay, so I can make up cases why maybe we're going to see differences in borrowing behavior for different groups. I don't need to get into that. I'm not looking for a theory. I'm just looking at the data and seeing what does the data tell me. So I'm going to go back, and I hopefully did this in Excel. So I did that one, and there I go. Oh, okay. And again, this thing doesn't want to let me zoom easily. I'm not sure why. Okay, so anyway, what I did back here with this data set, I asked for my residuals. So I went and I selected all my residuals, grabbed all these guys, copied them, and I pasted them over here, okay, into this column, which is really tiny. And then I pasted from my original data set. If I go back to it, way back here, I had gender, student, married, ethnicity. So I grabbed this data. Let me make this bigger. That's strange, it won't let me zoom. That I went and copied it into that sheet, if I can find it again. This one should be on Top Hat. This data file, it's Chapter 7 credit data. And so what I did was I took this I'm going to go through and repeat how to do this. I'll take the residuals that generally I don't take the label for this chart. I'm always nervous about taking labels. I can always add labels to charts, so I don't generally pick them. It asks recommended charts. No, I went to all charts and I picked box and whisker. Clicked OK. Okay, so you can see my chart here. Oops, make it bigger, please. There we go. And here's where most of my customers are, that I've got outliers that are up here that I am just going to change things. Right, like I did last time. I'm going to take no fill in this. Yeah, it didn't do it to me. Hold on. No, I want the outline. Excuse me. Shape fill. There it is. Get rid of that guy. Okay. So it's not as pretty, but it gets, you can see this is where most of my data is. And that the X, that's where the average residual is. It sits at 0. And this chart is a little bit below 0 because these outliers are dragging up the plot. Okay, the median is below 0. And so now if I go into my chart and I click design and I go select data and I click on edit, I can add gender. So I just go and select all the males, females, all the way to the bottom, just that column. Click OK. And you'll see here, hopefully, that it's populated male, female, male, female, male, and so on. I click OK. And this gives me a male box and whisker chart and a female box and whisker chart. They both look the same, really. They're not much different. And they both have this whole bunch of outliers. So there really doesn't look to be any difference between males and females. They're both very skewed distributions. There's the bulk here with a very long tail composed of outliers. I could have gone back here again, select data, go here to edit, and go, no, I don't want that group. I'm going to want a different group. And if I do married and ethnicity, here I'll just do ethnicity for one. Zooming down to the bottom here. And you can see it's already changed it. There it is. Caucasian, Asian, African American, they all look the same. So it's not changed anything for me. So, but if I was to go and pick student, turns out married gives me the same result. But look what happens when I grab students. Now, most people are not students. You probably can't see this column, but it says no, 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 no. The occasional yes. You can already see my chart over here. Look how it's changed. So let me, I'm going to make it blue. Oh, did it just to the outside. There you go. You can see my two box and whiskers here. And there is one outlier now. It's one student with a below average, I guess. But you can see I've got two very different groups. Here's the groups that are not students. They're balances. They're that big mass that's low down. And here are all the outliers. They were all the ones that were up here, plus a handful of ones that were down and they were mixed in with the mob here. So I've got two very, very different groups present here. And so if I can go and now, how do I deal with this in my model? Let me get back here again. What do I do with this? So here I show what I just did. It's a recap of that. So here were the box plots, and here was my student one here, that where they were really different. So students are where my outliers are. How do I deal with that? If you did quant one, you know how to deal with it. This is a categorical variable, and it's student yes or no. So it's a binary variable. And at the very end of quant one, you probably did capital budgeting and project selection, and where you were trying to pick, do you pick an investment or not pick an investment, 0 or 1. So a variable that, and I'm going to create a new one called student01. It's equal to 1 if you're a student, and it's a 0 if you're not a student. So what I did is I just used an if statement to create my new variable. So whereas before we've been taking numeric variables or variables that may have been coded as 0 for male and 1 for female, and we assign words to them, I'm going to go the other way. I'm going to take words and I'm going to assign a number to it. But the number is going to have to be a 0 and a 1, even if it was ethnicity. And let me go and show you ethnicity in a minute, because we're probably going to have enough time for it. So it's a binary variable. Binary variables I can put into a model that is yes, no variables. So I could have my intercept plus the thing with income and with rating and rating squared and rating cubed. But I'm also going to have student in here. And do I explain what happens here? Yeah. So think about this model here. If you're not a student, if student 01 is 0, you're not a student. This term is 0. So this term here would end up just becoming 0. And 0 times beta 4 is 0. So the whole thing disappears, right? So it's gone. If I am a student, then I'm going to put, whoops, I better go backwards here. I don't want to ruin my slide. If you are a student, I'm going to put 1 here. 1 times beta 4. Well, the 1 isn't important, but it means this coefficient that's here, this funny b that's there, reflects the difference between students and everybody else. Whoops, sorry here. What did I just do? Excuse me. I just jumped through my slides here. I'm forgetting I'm playing with my Excel file. Whoops. Now I lost it. And just scroll down. Okay, so if the variable is, if you are not a student, I get a 0, and it doesn't show anything in the model. If it's yes, then it says what's the impact of being a student. And so I put that into my data file. So what I ended up doing was I copied student over here and inserted that column. And then beside it, I inserted another column with an if statement. If F2 is equal to yes, put a 1, otherwise put a 0. And so I created a 0, 1 variable in here. And then I fit my regression model with all of these guys in it. So let's see. Is he here? There it is. So that here was that student 01. I put that in there. Oh, I put student, the word over here. And so I now got this block. So all I did was I went to data analysis, regression. Oh, electrician just arrived. We may lose our power. And so it's in column F. is where I put my predictor variable, and then my input range. Now I'm going all the way across to column E. And I had labels. I asked for residual plots. I asked my output range to be over here. Now I've got all the stuff, so I'm not going to show it. And so here I am. And again, will Zoom work on me? I wonder why it doesn't. Anyway, it'll show up on my slides in a minute. My R square, if you recall before, was around 89%. Now it's up to 97%, 0.9679. So it's really, really high. This is really close to 1. My standard error the last time with the squares and cubes got down to 150. Now it's 83. So that's a pretty big improvement. That's almost cutting it in half. So that was a really good improvement that I got here in it. Is that good enough for you? I don't know, but it's a lot better than what it was before. And it's updated my coefficients. Now, it didn't change them a lot. Remember, this was minus 9 point something. It's still minus 9 point something. But for rating, it was 4.3. It's still 4.3. Rating squared, I think, was 81, and now it's 78. Rating cubed was minus 21. Now it's minus 18. Look at this, 417 for student. What does that mean? It means, on average, students borrow $417 more than everybody else. Whoa, that's a big, big value, and it's probably changed things. The other thing that is really nice from a perspective of estimating things is you'll find the standard errors are now far, far smaller than they were before. They're cut in half, meaning that all of these estimates are twice as good as they were before. So the reason I may have had trouble estimating the impact of income or credit rating was because I had students mixed in there and they were disrupting figures. Okay, so let me show you. Oh, those are all the plots, but I probably got them in my PowerPoint. I can never remember what I put in it. So here was the comparison, and you can see the coefficients didn't change an awful lot between the two, which is really a good sign. That's every time when you're adding a variable, if you see big disruption in your coefficients, that's generally a multicollinearity problem. This is telling me, no, this is just straight improvement. It's giving me stuff I didn't know before at all. And these standard errors, this column here, I know it's a foreign concept to you and you probably don't appreciate it. From my end, this is amazingly good news that these became so much smaller. So my model is 10 times better than what I had previously. It's a lot better from many different perspectives. And my residual plots, here's my rating one. Okay, still, it's got a twist to it. There's something going on. There's something I didn't capture. I'm not sure what to do about it. But look at my income. It's perfect, and the other guys. There's a scatter that was up in the air that's gone. The blob that I've got here, it's neatly centered at 0, not too far above or below. This one, right around 0. These are all good news stories. I've got something strange here. I've got a group of 5 people with low incomes, very low credit ratings. They appear to be students. So I've got 5 low income, low rating students that are behaving differently from all the other students. Here are the students, most of the students here. These guys are outliers, really, from among the students. But other than those 5, out of the 400 customers, 395 of them are not outliers. They're nice. It looks like I'm getting good predictions. So this is a good model that it's now at the beginning, I was asking, what is good in terms of performance? You can say, hallelujah, I've got an R square 97%. I never see those. I've never seen one in practice. Uh, but, and this isn't real data, you're not going to get this sort of R squared in your assignment. You're not going to be able to predict house prices this well. But that my standard error now, if I'm putting it in concrete terms, I started out saying, yeah, if I want to predict credit card balances, don't be surprised if my error in prediction is $232. It may be $464. That was massive. Now I'm saying I can predict most of the time within $83, and very few of my predictions will be off by more than $166. That's a big improvement. That I've cut it down to a third of what it was at the start. So that's a much better model than I had. I've only got 5 people that are strange, and I should still look into them. Just like looking into the outliers that I had, I found they were all students. I discovered something that was a bit of a surprise, that students are vastly different in terms of credit card balances that they've got. They can't pay it off, is basically, it may not be that they borrow more, it's just that they can't pay it off. That I can do that causal analysis with respect to student. I can't really talk about income and rating and that type of thing. I can say that when I'm looking at these students, I've already adjusted for their income and their ratings. So if some of them were full-time students and had very low income, or some were students that spent the summer, well, right now, actually, out lobster fishing, if you're down on the South Shore, and had very good incomes, and then spent the fall term at school, that, okay, they've got really good incomes, but I've adjusted for that income thing. And so in addition to that, they exhibit this issue of uh, typically carrying a balance of $400. And as I said, my standard error is significantly reduced. That's usually, if you see that happening, then something really good has happened in your model. If you get multicollinearity, often that drives up the standard error because of the confusion among the variables there. It's hard to separate them and measure impact of each. That big standard errors are a problem for causal analysis. If it's in your prediction, that's a different thing. Okay? That all of that stuff you're going to look at in a formal fashion in a stats course. But in the stats course, the underlying ideas from an application perspective are staying the same with what you've got here. What you've learned in here is really all you need to know from an application perspective and do it reasonably well. Some people like to know the statistical stuff in there. For me, it's less important. That we'll move to it. I'm trying to keep things simple, and generally, when you're trying to explain to someone, you're not going to get into that type of thing. So, what have we learned through all of this? That we started out trying to estimate credit card balances and maybe understanding why some are big, some are small. So that was a value estimation problem, and with some causal analysis type objectives thrown in there. That we looked at initially, if you got a good rating, you're going to borrow more. Okay. But we also found, yeah, that's tied up with giving them higher credit limits. It came along with better income. That, in fact, we couldn't separate income from rating. So rating takes into account other types of credit issues, not just income. But it does include income. So they're interconnected. Okay. And so this is a problem we call multicollinearity. He's cutting holes in the wall. I can hear the electrician going to work. No. Anyway, that multicollinearity main problem is in causal analysis. For value estimation, it does have little problems, but they're not critical. They aren't showstoppers. For a causal analysis perspective, multicollinearity can be a showstopper because I can't explain what's going on. I can't explain income and rating separately. But for value estimation, don't worry about it as much. So, and in general, I'm saying keep things simple. And that's why we like linear models. Linear ones are nice because I can start explaining coefficients. I can say that as well, at least if I don't have multicollinearity, I could say as your rating goes up by 1 point, your average balance went up by $2.57. I could say what the impact of changing one is. This is going to happen. So if some of them were variables you could control, like how many times you put an ad, um, how often it appears online, and what the outcome is, then I can say, hey, having more frequent ad placements adds this much more to my revenue. So I can talk about that type of thing. And if it's linear, it's easy to explain, hey, that increasing the frequency of ad placements increases revenue by this much. And that's very valuable, and it's, again, easy to explain. Curves, you'd be saying, well, the first ones give you a big return, but the next ones don't give you a big return. It gets complicated to explain all that. Start with simple. It usually works better. Curves, once you get into it, you're going to keep it simple as a curve. I suggest generally making z-scores because the units of measurement can often be really ugly to deal with. I should warn you, once you get into curves, causal analysis is probably out the window. It's hard to explain a curve to somebody else. You can show them a curve, but as a picture, but in words, yeah, it's really hard. It's trying to explain stuff in calculus, and calculus is the study of curves, and it's not easy to give a simple explanation, and you lose your audience if it isn't a simple explanation. But, in general, how many variables should you be using? It all depends upon the problem. I like to start with one and then add and add and add, and I keep adding if it improves the model. And if I stop improving, then I'm going to stop. Okay, and that's what we did before. We had rating, we added income, we added age. It added information. But then at that point, we stopped last class. This time I even threw age out. I should go back and look to see, does it really help? It didn't help much before, maybe a little bit though. As to which ones to add, I generally look at my residual plots and give me some ideas, and I look at correlations of variables with my residuals. That the residuals are such an important thing. It sounds like it's a word we don't usually use, so maybe that throws you off and scares you away from using it. But just think of it, let's learn. Learning from your mistakes is the best way you're going to get better. If you can't understand why you made mistakes, you're going to go back and repeat them again. So if you really want to improve, look back to see what you did wrong and why, and learn from it. That's what a residual analysis is all about. Just basic, simple, common sense. That and looking at residuals is looking at what your model couldn't tell you, what wasn't explained by the current variables. That looking at a lot of plots, maybe a lot of work. That if you were to go and plot your residuals versus the variables you haven't used, that's a lot of work. It's good work to do. We haven't done it in that fashion, but it's a useful exercise. We've been doing the lazy approach and just looking at correlations. It's just quick and dirty. And that's a good place to start too. Generally because they're linear correlations. So if I'm looking at what variables to add in a straight line fashion, looking at correlation is often an easy way to do it. And what sequence should I be adding them? I use a method, we call it a greedy approach. We look at adding the variable that seems to give us the biggest gain, okay, the biggest improvement. Um, so the ones that seem to explain the residuals the best of what, if I had to pick one, which one would be the best one to pick? When in Quant 1, assuming you did Quant 1, you did linear programming. And in behind the scenes, there's a technique called the Simplex Method that changes your solution. It goes and looks at one solution and changes and changes and changes. And it does it using what we call a greedy algorithm. It says, I can only change one thing at a time. It's an incremental approach. It changes one thing at a time. And it finds what's the best thing to change, which one will give me the biggest bang for my buck. It makes that change, looks, okay, can I do better? And again, does that. And when it can't find improvement anymore, it stops. And it turns out that's the best way to solve linear programs. But with regression, some people use different approaches. Some start out by building a theory, throwing in all the variables associated with the theory, and then keep the ones that seem to work and throw out ones that don't. I don't. Most of the time, I don't have a good theory. Not for why it's a linear model. Coming in with a formula like this, most of the time, it's hard to explain. Uh, I, I don't go by the theory approach. I let the data tell me this what to do. And now there is one thing we've been adding. Would you ever throw a variable out? Turns out, yes, you will. So suppose you add a new variable in, and it turns out that you had variables A and B in the model, and then you added variable C into the model. It may turn out that keeping just B and C, you don't need A anymore. You needed it before you put C in there. A may have been the first variable you put in. A was a good idea. And B added things. But once you add C, you didn't need A anymore. And the way you find that is by looking at those standard errors of the coefficients. And when looking at your variables, if you find one that has a standard error that was quite big compared to the coefficient, okay, and if it's quite big, if that coefficient possibly could be negative or positive, then try taking it out and fit your model again. Because keeping it in, it's saying it's really not contributing information. It's like keeping some old garbage around. Yeah, you want to save it for a rainy day, but it's taking up space and it may be causing you problems. So it's not unusual for us to keep adding variables, and then as we add, check back to see, do we really need to keep the old stuff? And it may be that after we've added a lot of variables that we're going to throw stuff out again. Okay? There are actually some people that start out by putting everything in and start throwing things out. I don't like that. That often, though, if you find a variable that its coefficient could be positive or negative, throwing it out, the performance in the model will not get worse. It'll stay the same. Okay? But now you've got a simpler model because it's got fewer variables. So if you can throw stuff out, do that. And again, when do we stop? Generally when we can't find ways to make things better. Okay? And this one here, I'm not going to sweat over these last few cases. I don't know what to do next. But I could go and dig deeper if I've got the time and the resources. There are a lot of debates about building models. There's no one way to do it. I've given you a process, a strategy, a framework to follow. That it's not based on any fancy theory or anything. It's just common sense in some respects. This keep it simple principle, and letting the data tell me what to do next. And I'm training things based upon my experience. That very often for a data miner to work through this, there are some risks that you take. Risk of overfitting, of reading too much into the data than is really there. And so generally what a data miner will do is, if they've got a big data set, you don't in your assignment 3, you've only got 86 houses to look at. But if you had 8,000 houses, 800 houses to look at, you might go and take 200 of them and put them aside. Take part of your data set and put it aside. It doesn't have to be a huge portion, maybe a quarter of it, maybe even 10%. And don't look at it, okay? Practice, train yourself on the ones that you know. So if I had 800 values, 800 observations, I'm going to study 600 of them that I've picked randomly to study until I really know what I'm doing. And then I'm going to test myself. I'm going to go and see, how does my model predict on the 200 cases that I never looked at. So we use that one to do that evaluation. We'll talk about that later when we get to evaluation, but that's generally the approach that's taken, so that you don't cheat by training things to overfit your data. Okay. So I've got a process. I want you to keep it simple, use as few variables as possible, keep it a linear function if possible. It's as simple as possible. That they look at your residuals to give you guidance. If you got curvature, maybe put in an x squared term. I went to an x cubed. Most of the time, people don't go beyond x squared. That if you've got pockets of outliers, then that's a suggestion you should look at groups. That maybe you have two groups of things. And so look at nominal variables, categorical variables to sort of explain that. And next class, we're going to get into trying to make predictions about categories. So here I've got a categorical variable, like student, not a student, okay, that I'm using to help predict credit card balance. The next model I could get into, I'm not going to focus on this, but actually I could do, is if you knew someone's credit rating and their credit card balance, could you predict whether or not they're a student? We saw students were quite different. Could I go back the other way and so try to predict a 0-1 variable from a numeric variable or something of that nature? Turns out there are a lot of different approaches for doing that. And we'll look at a variety of them. And this is your last Excel class. I might bring some stuff in later, particularly towards the end when I look at best practices with charts at the end of the course. But for those of you that don't like Excel, you can probably relax once you're through. I might have a little bit on assignment 4, but it won't be in any of the lectures for the most part for the next while. Won't be on any more of the quizzes. Will be Excel questions, I don't think. So this is sort of where we're going to end on that bit. And I think that's the end of my slides. So, but there was one thing I was going to just show you quickly. Let me, what would happen? Let me go back here to my data set. And let me just grab this stuff and put it in a new sheet. Oh, and I probably can't make this bigger, can I? No, why won't do that? Well, I'll increase the font size. Maybe I do it that way. Yeah. Okay, I'll cheat this way. Suppose I wanted a model that had balance equal to, and change font size to make this, oh, there, good, okay. I'm going to have an intercept, and I'm going to have slope 1 times rating, and then I wanted to have slope 2 times ethnicity. You can see that. Okay, so it might be it's going to be equal to minus 390 plus 2.57 times rating plus something times ethnicity. Now, it's not like student being 0, 1. This is Caucasian, Asian, or African American. They're 3 different values. Okay, how do you do that? Well, it turns out I can't. I can't do 1, 2, 3 because that would be saying that, or 0, 1, 2, because then I'm into scale things. 2 is twice as big as 1, or they're in a hierarchy, and I really don't. I just want them yes or no. What I end up having to do is having a base case. So I'm gonna have to make my words bigger again. Okay. Or maybe do this in a PowerPoint since I've been doing it that way. We add a new slide and I can type it in. Here's my little whiteboard. So what I'm going to have is a base case. It's going to be Caucasian or Asian or African American is the whatever. Then I'm going to have Asian 0, 1 equals 0 if you're not Asian, and 1 if you are of Asian ethnicity, big broad category. So if you're Caucasian, it's 0. If you're African American, it's 0. But if you're Asian, it's equal to 1. And then I'm going to have African American 0, 1 equals 0 if not, and equals 1 if you're African American. So my new model is going to end up looking like this. My balance is equal to an intercept, some number, plus slope 1 times rating. And then I'm going to have slope 2 times Asian. And I'm going to have slope 3 times African, 0, 1. And in this model, if you're Caucasian, if you're white, both of these will be 0. So it's just going to be intercept plus slope times rating. If you're Asian, it's going to have intercept plus slope times rating plus slope times 1. And this term will be 0. So this will reflect differences that would be for Asian heritage. And if you're African American, balance equals intercept plus slope 1 times rating. This will be a 0 because you're not Asian, and you'll end up with just slope 3 reflecting the impact of being African or African American. You can add these variables if I wanted, art, science, business into a model, fine. I'm going to have someone be a base case, say art, and I'll have a variable for business. Are you in business or not business, or in science or not science? Um, if I did it with your data and it was on survey stuff, I might need a lot of variables to reflect. Is your home in Nova Scotia, outside in Canada, outside Nova Scotia, Caribbean, Africa? Did I have South Asia, China, and other? So the base case might be Nova Scotian. And then I'd need to have a variable just for Canada outside Nova Scotia, another variable for Caribbean, another one for African, another one for South Asia, another one for China, and another one for other. So I'm going to describe home in a model, I'm going to have to add in like about 6 variables in here. It gets really messy and complicated, but we can do it. That's all I'm trying to point out. So with those, we can capture those sorts of things. And we may only find certain locations relevant and other locations not relevant because their coefficients are really big or not. So it may be only certain groups are outliers to our data and others are not. But basically, that's where we are. And anyway, I've gone over time now. I apologize for that. That you'll see me on Wednesday. And please try to do as much on the assignment as you can before Wednesday so that we can talk about Excel issues or interpretation issues. So they're both technical ones. I'm having trouble with Excel doing this. And on others, I've got it, but what does it mean? We'll talk about that. And we'll devote as much of the class as necessary to addressing assignment 3. And the material that we've got that's coming out of chapter 8, I can expand or compress. It's quite elastic, and it doesn't generally take as much time unless I get really long-winded, which I can do too. Anyway, you guys, if you're still there, bye-bye, Chris. Bye-bye, Ben, and anyone else that joined in the class. Bye-bye.